Okie dokie, I guess let's get started. So today's recitation, we'll start practicing with integration. So I think for today, we'll just focus on X and Y coordinates. On Friday, I can do some more practice with polar coordinates from section 15.3. But yeah, for today, let's just focus on X and Y coordinates. And so basically, just to refresh your memory, rectangles are the easy case for double integrals. So overall, my philosophy of double and triple integrals and everything is that essentially it's not any harder than it was in Calc 1, the actual solving of the integrals once you have them set up, because you're just doing a couple of Calc 1 or Calc 2 style steps in a row. You do the Y integration on the inside, then you do the X integration. It's just 2 steps. And so next week when we get into triple integrals, you'll see that that's really the same story for triple integrals as well, that it's just a third step along the lines of what you've done before. The tricky part, the reason why we have to spend a whole chapter talking about multiple integrals, is that getting the bounds, that is trickier. That for double integrals, it's trickier than single integrals, and then for triple integrals, it's somewhat trickier than double integrals. So it's all about the region of integration and the bounds. That's sort of where the hard work has been moved to. But once you get the bounds, it's pretty much good to go as far as ideas you learned back in Calc 2. And so the easy case, the regions for which it's easy to get the bounds set up, for double integrals, that's going to be rectangles. So rectangle, x goes from a to b, y goes from c to d. And when you set it up like that, it doesn't really matter which way you do it. If you do it dy dx or dx dy, basically just make sure you keep them in order. So the inside goes with the inside, the outside goes with the outside. I think physicists do this backwards. They're jerks. Doesn't make any sense, but for us, this will be the convention. So C and D goes with Y, A and B goes with X when you do it like that. Okay. And so rectangles, dy dx, dx dy, doesn't matter. You're good to go. And so unfortunately, when you're not dealing with the rectangle, you're going to have to do more work. So if it's not a rectangle, you won't have all numbers as your bounds. You'll have to have some variables somewhere. And so as far as just to refresh your memory of where the variables can go, which types of setups make sense, the number one cardinal rule for this is that the answer has to work out to be a number after you do the iterated integral. So by a number, I'm not talking about scalar versus vector. I'm talking about variable versus constant. So your answer has to be a number, not a function of x and y. Because it's just like in Calc 1, when you learned what the definite integral from a to b of f of x dx was, that was just a number. It represented the area between the x-axis and the curve y equals f of x between x equals a and x equals b. It didn't, no x's were on the right-hand side, because remember, what do you do to do this? You, of course, take your antiderivative and plug in and subtract. So, yeah, big F of b minus big F of a, those are just numbers. There's no x's anymore. So essentially, when you're setting up a double integral, that's the number one rule you want to make sure you follow, that your answer works out to be a number. So something like this is really bad, because remember the iterated integral step that Dom went over the other day? You work your way from the inside out. So, if you were to do something like this, you would first do the partial antiderivative with respect to y, plug in d and c, and then you'd get some stuff. And if you were plugging in h2 of y as your last thing that you do, that y is, of course, going to hang out in your answer. So your outermost bounds cannot have any variables in them. And then you go through and think about, okay, well, where could variables occur? What does it work out to be? And so it turns out that, yeah, for dy dx, it's okay to have x's in the y bounds. So that's why I have this g1 of x, g2 of x. And as far as keeping track of what those mean, as far as the region goes, for dy dx, it's basically the inner y bounds are the bottom and top curves for this region D. So again, double integrals, we're always doing it over some region D in the xy plane. And so when you go to draw D, you have this bottom curve, y equals g1 of x, and you have this top curve, y equals g2 of x. And so those are what the inner y bounds represent, the bottom and top curves for your region. And so it's not so important, but we can call regions that we could do with one dy dx integral type 1 region. So I'll show you an example of when wouldn't necessarily be type 1. But anyway, that's the situation for dy dx. For dx dy, it's really the same picture, just kind of rotated. So now the idea is that you have your left and your right curves. And so you think of the region D as starting at the left curve and stopping at the right curve, like that. And so notice we're always, when we're setting up multiple integrals, going to have our lower bounds smaller than our upper bounds. So that's how you can remember that essentially the left curve goes with the lower bound and the right curve goes with the upper bound, because as you move from the left to the right, x increases. So that's how we want to do that. And so then, yeah, that's the idea. And so regions that you could do with one dx dy integral, we're going to call that type 2. And then it's kind of like blood type, where regions could be both or neither. They're not mutually exclusive. So a region could be type 1, type 2, both type 1 and type 2, or neither type 1 nor type 2. And again, it just refers to if you have to split it up or not. So a couple of the examples I'll show you in a second, that'll make sense for that. So when you're not dealing with a rectangle, you gotta have variables in the bounds. And this is how you figure out which variables go where. Okay, so let's practice some. Let's do the double integral y dA, where d is the region bounded by y equals x minus 2 and x equals y squared. So it's all about getting a picture. So, obviously, we can't require that you draw a picture for these questions on quizzes or tests, but it's really in your best interest to draw a picture so you can really figure out what's going on precisely. So it's all about getting a good picture. So y equals x minus 2, that's slope 1, intercept negative 2. And then x equals y squared is going to be a parabola opening to the right from 0, 0. So the region bounded by this line in that parabola seems to be this shape here. And so what we're going to do is I'm going to show you how to do this in both dx dy and dy dx, and we can decide which way is better. So let's actually do dx dy first. So dx dy, before I do this, let me copy this and make a duplicate for when we do dy dx. So dx dy, it's all about left and right curves. Whereas for dy dx, when we get to that in a second, it's all about bottom and top curves. Okay, so left and right curves. It looks like the left curve for this region is the parabola, and the right curve is the line. And so these left and right curves, we have to write them x as a function of y, right? This is what we did on the previous slide. And so sometimes that's all ready to go for you. That, yeah, the parabola is already given to me x as a function of y, x equals y squared. However, the right curve is not quite given to me in that form, but it's pretty easy to move things around and see that x equals y plus 2 is the right curve. So essentially, those are going to be our x bounds on the inside. So we'll have y squared on the left, and then y plus 2 on the right, y dx dy. And then the outer y bounds are just all the y values that we see. So I suppose we're actually going to have to solve for the intersection point of these two curves. So let's figure that out. Well, if y is x minus 2, then x equals x minus 2 squared is the intersection. And so, okay, x equals x squared minus 4x plus 4. So x squared minus 5x plus 4 equals 0. So x minus 1, x minus 4 equals 0. So x equals 1 or 4. And so, okay, this must be then, if x is y squared, this is the point 4, 2. And then if, yeah, and then this is the point, so y is plus minus square root of x. We figured out, yeah, if y is x minus 2, this is the point 1 minus 1. Yeah, so those are our two intersection points. And so that's our values for y. Y is going to range from -1 up to 2. So maybe I'll move this out of the way so we can actually do the integration in a few minutes. But that stuff was just sort of, yeah, find the intersection of the parabola and the line. Not a huge deal. Should be, you guys should be okay with that. Okay, but then let's just practice doing it dy dx. So dy dx is actually going to be a little bit more of a pain, because we see that the bottom curve sometimes is the parabola and sometimes is the line segment. And so basically, this is going to be not a type 1 region, because the bottom curve changes. It is type 2. We were able to do it with a single dx dy integral. But for dy dx, we're actually going to have to split this up into 2 pieces. It's not the end of the world. It's just a little bit more tedious. So it looks like no matter what, so the top curve is always the parabola. Remember, the parabola was x equals y squared. Well, the top half of that, so if x is y squared, y, of course, is plus or minus the square root of x. So the top half is given by plus root x. And the bottom half, which over here, that's going to be y equals minus square root x. And then here, this is y equals x minus 2. So essentially what happens here is that for a while, the bottom curve is the bottom part of the parabola and the top curve is the top part of the parabola. And then for the rest of it, and remember, we already figured out that this was 1 minus 1 and this was 4, 2. So for x between 0 and 1, that's what was going on. But for x between 1 and 4, the bottom curve is the line and the top curve is y equals square root x. So notice everything about rectangles is simpler. First of all, getting the bounds set up is simpler for a rectangle, but also in a rectangle, the dy dx and the dx dy, they basically just flip. You don't have to do any hard work to change the order for a rectangle. So first of all, you might wonder, okay, yeah, is this equal to y squared to y plus 2 minus 1 to 2 y dy dx? No, 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 no. Because that violates our number one rule, that there's variables on the outside bounds, which you think about the iterated integral procedure, those variables are going to be in your answers. So first of all, that gives us total nonsense. You know, our answer has to be a number, not a variable. And moreover, more complicated things can happen with non-rectangle regions, that you might have something that's, for example, type 2, but not type 1. That, okay, it turns out that this setup is equal to this. So how on earth are you going to figure that out just from looking at this and trying to figure it out? So it's really about getting the picture. Then I know some of you think you might be able to have the picture in your mind and figure it out like this, but I don't know, this is pretty tricky. I really suggest that you draw and practice drawing and practice thinking all this stuff through. Because yeah, as it turns out, this dx dy looks like it's a little bit easier. Dy dx is possible. You just have to be careful because of the fact that the bottom curve changes. And so again, you know, the worst thing you could do is think that the bounds are all numbers. So I know some of you might be, the naive way to do this is once you have the picture, say, oh yeah, x goes from 0 to 4, y goes from -1 to 2. No, that's not right. For this region, that's a rectangle. That's what I was saying a few minutes ago, that the only time your bounds are all numbers is if you have a rectangle. And so if not, you have to have variables in your bounds. It's trickier, and this is the type of thing you have to think through. So that's the setup. And I might as well calculate this just for extra practice. But at this stage, that's the hard part, like I was saying a few minutes ago, because now we work our way from the inside out. So we do the I guess I should call it the partial antiderivative with respect to x. So if I pretend y is a number, what's the antiderivative of y with respect to x? Well, it's xy. And so then I'll plug in my x bounds, which are y squared to y plus 2. So I get -1 to 2 of, well, if x is y plus 2, this is going to be what? Y squared plus 2y minus y cubed. And then at this stage, it's just a Calc 1 type question. So what? Y cubed over 3 plus y squared minus y to the 4th over 4 between -1 and 2. Whatever that ends up being, what? 8/3 plus 4 minus 4 minus -1/3 plus 1 minus 1/4. Whatever that ends up being. And the dy dx, of course, you'd get the same thing. But yeah, it's really all about the bounds. And it's all about drawing the picture to help you figure out those bounds. Okay, and so obviously, some questions you're not going to need to do both dy dx and dx dy. And so some questions, when you're making your decision which way you want to do it, sometimes the region influences your choice. So that's what I'm going to write here. Sometimes the region influences your choice of dx dy or dy dx. So some regions you have to split them up to do them in a particular order. Whereas other orders, they might be a little bit simpler. So this is type 2, not type 1, which means that dx dy is probably a little bit easier. Okay, but let's look at another example. So y squared e to the xy, where d is bounded by y equals x, y equals 4, and x equals 0. So y equals x is that line. Y equals 4 is a horizontal line, and x equals 0. So it sounds like, and be careful, just sometimes if you go through this a little too quickly and aren't careful with your drawing, you might end up with sort of the complementary region. So we don't want that here. That would be, so this region would be y equals 0, x equals 4, and y equals x, but just read carefully, we want y equals 4, y equals x, x equals 0. Those are our three sides. So anyway, that's our region of integration, this triangle. And so we want our bottom and top curves. This intersection, of course, happens at the point 4, 4. Okay. And so for dy dx, our bottom and top curves look like that. So y equals x is the bottom curve, y equals 4 is the top curve. And so our y bounds on the inside for dy dx are x to 4. We're starting at the line y equals x, we're stopping at the line y equals 4. So we have that, and then this occurs for x between 0 and 4. So, okay, let's, for practice, do dx dy. Might as well have just redrawn that from scratch. So for dx dy, you're doing left and right curves. Okay. So what's going on here? It looks like our left curve is the y-axis, x equals 0. Looks like our right curve is the line y equals x, which, remember, for dx dy, you have to have your curves in the form x in terms of y. Well, it's pretty easy. If y equals x, x equals y. And so it looks like our dx dy bounds are 0 to 4 for y, and then 0 to y for x. Okay. And so as far as which one's better, sometimes how do I want to do this? Sometimes the integrand influences your dy dx versus dx dy choice. But for the most part with rectangles, when your bounds are all numbers, there's nothing that sort of interesting that the bounds can do when you plug in and subtract on the inner step. That essentially, if you are practicing a lot of these with rectangles, if you do a rectangle dy dx versus a rectangle dx dy, it's usually the same exact steps, but just in a different order. That with rectangles, yeah, nothing really complicated comes into play from these inner bounds because they're just numbers. However, for non-rectangles, when you have variables in your bounds, they can interact with the antiderivative steps that you have to do to actually calculate this out. And so for non-rectangle regions, the work that you have to do to calculate it can be quite different depending on whether you do it dx dy or dy dx. And so now for this, I picked one where it's actually fine both ways, but if you carefully think about what's going on, there's one way that's at least easier to get started, and it turns out it's a little bit easier to finish. So let's think about the first step for each of these. And so it has to do with looking at the function y squared e to the xy and deciding, is it more complicated if you think of x as a constant or if you think of y as a constant? And so it turns out I think it's easier if you pretend y is a constant, because if I'm trying to do y squared e to the xy with respect to y, antiderivative, you need to do parts twice. So if you remember back to 141, you know, something like x squared e to the 2x, that's what you would need parts twice to do. Because you basically have two extra factors of x. And so, yeah, if you want to do that, that's that. As far as this course goes, 230, 232, we don't really like to force you to remember how to do integration by parts. So most of the questions we'll ask you to do on quizzes and exams, actually all of them, you'll be able to do without integration by parts somehow. But for this one, you could do it with parts twice if you do dy dx. But for something like if you pretend y is a constant, so antiderivative with respect to x, it's really a lot easier. Because if I'm pretending y is a constant, I'm looking like, what's the antiderivative of 9 e to the 3x? Like, it's easy, right? So maybe you guys on your own could practice, practice this. Make sure you get the same answer. But let's do this one instead. So if I'm pretending that y is a number, then as it turns out, yeah, the antiderivative with respect to x is just going to be y e to the xy. It's just sort of straightforward, easy substitution. And so I would get then 0 to 4, y e to the y squared. And then be careful, if x is 0, we actually get that. And then it turns out you don't actually need integration by parts for this. You just do a substitution on that first term, u equals y squared, and then get that. And so it looks like we get what? E to the 16th over 2 minus 16 over 2 minus 1/2 minus 0, right? Because e to the 0 is 1, be careful. And so with this triangle region was equally easy in either order. This region is both type 1 and type 2. We don't have to split up either of them. But if you look at what you have to do to get started, y squared e to the xy dy, that's a little bit trickier because you got to use integration by parts twice. But if I do the dx first, I end up having a little bit easier time. And so, yeah, with rectangles, it tends to be the same step. So like if you need parts with one order for a rectangle, you usually do for the other order as well. It just sort of moves around where those steps occur. But with variables in your bounds, it can really make the two different orders work a lot differently when you go to actually calculate it. Okay, so one last example. Calculate 0, 1, 3y to 3 e to the x squared dx dy. So hopefully you guys aren't too rusty on integration. What always a lot of people do, and you really shouldn't do, is okay, the following is bad. You get 0 points if you do this, is thinking that you can integrate e to the x squared with respect to x. That doesn't work. The derivative of e to the x squared over 2x, you take the derivative, you got to use the quotient rule, and you're not going to get e to the x squared. So, like I said, we're not really going to we're not going to worry too much about some of the trickier integration techniques from 141, for example, parts, trig sub, partial fractions. We're really not going to need any of that for this course. But what you should remember is when you just straight up don't know how to do something, because that's something you talked about in 141, that integration is hard compared to differentiation. For derivatives, if I give you a formula, you could always find the derivative using a combination of chain, product, quotient, all that fun stuff. But taking an antiderivative is more difficult and sometimes impossible. And so some functions don't have antiderivatives whose formula we know in the traditional sense. So it turns out, yeah, if your function's continuous, it has an antiderivative. We might not know the formula for it, though. So e to the x squared is an example of such a function that it has an antiderivative, but as far as the formula goes, you could either do a power series or you could just define the antiderivative of e to the x squared. But as far as actually calculating it, writing down a traditional formula for this antiderivative, we are just completely and totally stuck. So make sure you go back and practice some substitution problems if you feel that you might be rusty. But honestly, just think about, reversing the steps of derivatives that we've done. And just remember that, yeah, not all antiderivatives you're going to be able to do. So e to the x squared dx, we're giving you a big hint here. And so it's up to you guys to realize that this is a hint that we're stuck, that I don't know the formula for antiderivative with respect to x of e to the x squared. And so again, for this course, I think substitution is going to be about as far as you need to check. Because, okay, if I want to do antiderivative of e to the x squared, I would try u equals x squared, and then du equals 2x dx. And I don't have this. So we don't have the derivative of the inside that we need to make substitution work. You just pretty much get stuck. So I guess what you could write this as e to the u over 2 square root u du, but good luck, you're stuck there too. So some functions you're just not going to be able to find an antiderivative of. It's actually kind of neat. It's not that no one's discovered one yet, but you can concretely define what it means to have an antiderivative formula in the usual sense, and you can actually prove that this function doesn't have one. So it's one of those neat things in math that not only has no one found a formula, but they've actually shown that no such formula exists. So anyway, if your substitution doesn't seem to work out, that's a hint to try something else. So what else can we try? So that's a hint to try something else. And so really the only two things as far as this course goes that we could try, I guess there's like maybe three things that, you know, first of all, maybe there's, well, okay, so polar coordinates, that's from section 15.3. I guess you could try dy dx, and then is there some kind of symmetry or some kind of geometry such that we already know this answer? And so I'm going to show you some of those tricks on Friday, most likely. But anyway, what could come into play here? So polar coordinates, as you saw yesterday, was all about when you have disks or portions thereof. Essentially, polar coordinates are good when you have something involving x squared plus y squared, whether that's in your integrand or whether that's in your region. That x squared plus y squared turns into r squared for polar. So that's what you're on the lookout for that. So like I wouldn't say anything here. There's no circles. For dy dx, well, that is going to be what we end up doing. But for symmetry and geometry, yeah, so on Friday we'll talk about either odd symmetry or just there's some, because at the end of the day, remember, double integrals are volumes under surfaces, so maybe there's some surfaces whose volumes you can recognize as sort of a shortcut for doing this, but the surface z equals x squared, I don't know what the hell that, I mean, it doesn't look that complicated, but I don't have a simple volume formula for something involving that type of shape. So anyway, really the only thing, if we're asking you a question, there's going to be a way to do it. So anyway, it turns out that dy dx is going to be exactly what we need to do. So I really like this type of problem. It tests that, first of all, you remember that there's antiderivatives that we get stuck on. But second of all, you're going to have to draw the region from the bounds. So you're going to have to show that you understand how to look at the bounds and figure out the region. Then you're going to have to do the other bounds from that picture. So this is testing a lot of different ideas. So it's a really neat question. So anyway, let's draw the region. So now we're kind of going in reverse from the skills that we were talking about a few minutes ago. So what are those bounds telling me? They're telling me that x equals 3y is the left curve. It's telling me that x equals 3 is the right curve, and that y is between 0 and 1. So let's draw that picture. What does x equals 3y look like? Well, it's a straight line through the origin. What does x equals 3 look like? Well, it's the vertical line, x equals 3. And these two intersect at the point 3, 1. And so they say for y between 0 and 1, you start at x equals 3y, you stop at x equals 3. So this is the region that we're looking at. It's that triangle. Okay. So now let's try to do it. Now I'll just start over because I have to erase a lot of stuff. So now we're going to try to set it up dy dx. So as far as dy dx goes, I haven't really explained why we're tempted to do this. Well, we're tempted to do this because we're completely stuck. But if you think about it, if we are able to get this set up dy dx, I can at least do that first step. Because in the previous example, which variable you're treating as a constant can really affect the difficulty of the antiderivative. So e to the x squared with respect to x, I'm 100% stuck. But e to the x squared antiderivative with respect to y, well, that's easy. If I'm pretending x is a number and y is my variable, then my antiderivative is y e to the x squared. Okay, and so let's figure out these bounds then. So it's going to be the same triangle. And okay, so for dy dx, we're doing bottom and top curves. So y equals 0 seems to be the bottom curve. Y equals x over 3 is your top curve. And then this occurs for x between 0 and 3. And so what do you know? The bounds give us the factor that we were missing for a substitution. So after you do this so at first, I'm not sure that I'll be able to finish this, but I know I'll at least be able to get started. But then as it turns out, this region works out so nicely that, yeah, this x is exactly what I need to make a substitution work. So if you do u equals x squared, 1/2 du is x dx, then this antiderivative is basically going to be e to the x squared over 6. Evaluate between 0 and 3, so what? E to the 9th minus 1 over 6. So as far as calculating by hand, we can have, for example, dy dx doable by hand, while dx dy is impossible by hand. So again, like, yeah, if you had a computer, it could numerically approximate this in either order without much trouble. But as far as antiderivatives and things like that go, you could get completely stuck with one order and have success the other order. So anyway, there's a few on the homework that are like this as well. But I think that's all I had planned for today. So have a good day, and I'll see you later.